Okay, guys, welcome. We are now proceeding to our next talk of this block, and it will be given by Pavle Kecman, who is a data scientist at IBM Advanced Analytics, Global Business Service. He is experienced in building and deploying predictive and prescriptive models. His talk will focus on several experiences from different industries: banking, insurance, and manufacturing. In each example, the primary machine learning model was extended with an optimization or natural language processing module to improve the prescriptive power of that model, simplifying interaction with end users and ensuring smooth integration in organizations' operational procedures. So without further ado, I would like to invite you to give a round of applause for our next speaker. Thank you.
Hello. My name is Pavle Kecman, and I am very happy to be here. I work in IBM Amsterdam for the past few years. I worked in IBM in Amsterdam as a consultant doing cross-industry, basically data science, applying in different industries, supporting different clients, etc. So basically, I'm very happy to be here today to give you some of the insights that I have acquired over the years working with different clients with different industries. And in particular, I would like to focus to what I call here the real world. So to first take a minute to explain this a bit cryptic title of the presentation. By real world, I would mean the traditional industries, the offline world. So in particular, in relation to data science, that would be the world where the output of a data science project, so the let's say machine learning model, is finally being used by a human operator. So it is still the human operator who is making the decision, and machine learning model is typically used as a decision support. And in many industries, in many traditional industries, this is still the case. So apart from online world, apart from web companies, primarily the machine learning models are still being used as decision support system to the decision makers. So this will be the main topic of my talk, but let me begin here with the previous speaker mentioned this CRISP-DM framework for data analytics. And to be honest, it has been in every single presentation that I'm giving about data science, it's still there. And every time I make a pledge that I will not put it anymore, and somehow last moment I always include it. So why I put it here? It is a framework that is basically describing the high-level steps that each data science project has to take to be able to be deployed in practice. So the focus of the framework is to start from a very early business understanding of the business problem until the actual deployment. So not to finish with a PowerPoint presentation, but to deploy it in the IT architecture. However, and this framework has been challenged a lot, that it's not granular enough, that it's not detailed enough, that the arrows do not represent processes very well, that not all the loops are very well connected. But I'm going to challenge you today from a bit of a different perspective. So I'm going to challenge it whether it really ends here at deployment or whether there should be maybe another step that we need to consider. So basically the main topic of my work will be that the indicator of usefulness of the machine learning models that we provide is not mainly this evaluation step in CRISP-DM, but the true indicator of usefulness is how it is used and whether it is used, and how it contributes when it is adopted by the end user. So in that sense, let's take a step back and talk a bit more what evaluation of the machine learning model really means and how it is perceived by different participants in a data science project. So evaluation from a perspective of a data scientist is simply evaluation of metrics. So the previous speaker also mentioned metrics. There were questions about the metrics, and we typically would focus on metrics that are dependent on the nature of the problem. So classification problem, clustering problem, regression problems, they would all have their own metrics, and we as data scientists are pretty narrow-minded and focused on that to boost those metrics, as if we are competing in a Kaggle competition, but the fact is that we are not. Then the business owners, we present our models to the business owners, to people who actually invested in us developing that model. And basically the only way that they evaluate that model is how much it increases their KPIs. They have been working for a long time with their business problems. They already have the strict KPIs, and the only thing they want to know how our model will affect them and whether there will be a return on investment on that. But what is the steps that are often neglected is how these models are adapted by the users and how users are going to evaluate those models and how if they will appreciate it enough, if they will use it the way they're supposed to be used. So in that sense, I have listed here a few different aspects that users would typically, that's from my experience, and this list is by no means exhaustive, but these are, according to me, a few main, let's say, issues that the users are focused on. So first of all, this would be user friendliness. So how easy it is for the user to interact with the model. And to that step, we've come a long way from depending on software engineers, because now our users can develop pretty nice applications and user interfaces in Shiny. Python users can use Flask, can build a Flask app to make it easy to interact with their model, etc. So in that sense, let's say we have this topic covered as data scientists. Second issue and second criterion for evaluation was being heavily addressed here in the second keynote speak. It's about transparency and interpretability, and or we can say explain whether the model can be explained and interpretable. And there are the mentioned Lime package, which really simplified this interpretability and increased the potential to interpret the model. And to that, I would only like to add this recently newly developed package called SHAP that kind of also increases the power of Lime and gives some kind of mathematical proof about what are the main driving factors behind certain model decisions. So we can say that this topic is being heavily addressed, and we almost have it covered. So then perception of the model, how the users perceive the model. Because when we build the model, we build the model based on the large numbers. So based on a huge amounts of data, and then we give KPIs that are a result of these aggregated some kind of aggregated metrics, right? While the user, they always have this negativity bias, and they always they perceive it that the Murphy's law is running behind the model, because when they want to use it the way they would, it sometimes doesn't go wrong, and then there's a huge negativity bias, and they develop a kind of resistance towards the model. So this is something that is like intrinsical a situation that we have to deal with, and there's no easy way out for this criterion. And lastly, the last two criterions are pretty much the ones that I'm going to address today. First one is that our models are too greedy often. So we are given in large organizations are very complex and interconnected, and changing something in one part and one department can have a domino effect and propagate either positive or in a negative way throughout the whole organization. And we are typically employed by a single department that we try to help, but at the end we make damage on the other. So typical example would be, for example, propensity models that are product oriented, and which then may lead us to the fact that we are over-promoting a single product, while that product is kind of cannibalizing all other products, etc. So this would be just one example of this models being too narrow-minded and too greedy and too aggressive, instead of looking at the global perspective, organization-wide perspective. And finally, the last one is, I really didn't know how to translate it, and translating idioms is not really the easiest thing to do. So it's about bear favor, and this bear favor in Serbian language it exists in many languages, but not in English, unfortunately. But let's say the background of the story is that the man and the bear lived together, and they were super friends to each other, and they helped each other. And then one day a bee lands on a man's back, and bear really wanted to help his friend, tries to kill the bee, but unfortunately, I mean, bear is too strong, so it had some negative effects. So I think in English it would be that the road to hell is paved by good intentions, but I prefer this bear favor much more. So what I mean by bear favor is that we produce a model that at the end creates more work, or it doesn't save as much work as it should. And that's also a thing that we need to, and that's also a thing that may discourage the users from using the model. So in this talk, I will give two examples about how really developed data science model can be problematic for users to accept. So in the first example is related to an insurance company where we developed a model that at the end fulfilled all the criteria, all the evaluation criteria from CRISP DM framework that I mentioned at the beginning. However, it was extremely difficult to use, and we needed to do a lot more work and still apply additional data science model in order to make this model friendly. The second example is a company that it's a bank, it comes from banking. The bank was focused on maximizing their client lifetime value, and they were quite aggressive in building models. They created a whole bunch of propensity models, churn models, etc. And at the end, the results were not as expected. Each model individually performed really well, but at the end, when they deployed it, when the user starting and then the relationship management started being run by that sequence of model, it didn't go too well. So we did another approach, a bit more globally oriented approach, and I would like to explain that as the second example of this talk. So the first example is based on bodily injury claims. It is very, let's say, very hot topic in insurance company, and there is a sense when there is a bodily injury claim. So first I will explain a bit of a business background of the problem. When there is a bodily injury in insurance, insurance companies, apart from covering the third-party liability for material damage, insurance companies also need to recover all, let's say, effect on life for the injured person. So that doesn't mean necessarily like covering health expenses, because for that there is a separate health insurance, but that means covering all, for example, income loss, inconvenience loss, the fact that we are missing out, that the injured person is missing out on hobbies, has to do household work, etc. And these claims are very, very long, and they can be extremely costly. So it is very important for the insurance company to have an estimate how much each of these bodily injury claims will cost, so that they can reserve enough funds that they can have for accounting purposes and actuarial purposes, that they can have a good estimate on their cash flow. Secondly, these bodily injury settings for claim handlers, for human operators, are extremely difficult to handle. They require a lot of paperwork, and they require a lot of information that doesn't come at the same time. And our goal there was to take the information about the bodily injury and try to present the claim handler with our estimate of how much that claim will cost. So on the one way, that estimate will be used for the, like I said, global accounting purposes of the whole insurance company. On the other hand, it will be used by the claim handler to kind of have an estimate what the claim will cost and to try to settle the claim with that amount. And so this problem is, yeah, maybe we can skip on the fact sheet, but the nature of this problem is kind of it's very, very Bayesian in nature. What I mean by Bayesian is that not all information is present at the same time, not all information is reliable, and basically everything we know about a bodily injury keeps changing, keeps getting updated. So initial diagnosis can get updated. At the beginning, we don't know much about the person's income, profession. Also in the beginning, we don't know much about the treatment that is being deployed, etc. So this all evolves over time, and we keep receiving that information as the time goes by. So that's why we build this Bayesian network framework, where basically at the beginning we have just a notification of loss for the particular claim. We run our Bayesian framework that the most interesting, let's say, connections within the Bayesian network are presented here. And over time, as new information becomes available about the claim, we simply update one of the nodes in the Bayesian network, and all the posterior probability distributions are updated. And the model performed really well. We were super, let's say, we really tried hard to encode all the decision-making procedures of the claim handler. And the model was being evaluated and accepted. But then when we actually came to deployment, because the model was developed based on the archive data. So we deployed it into production environment. And what we saw was that almost all the information that we needed for our network is empty. So the claim handlers do receive this information. The insurance industry is heavily dependent on documents. So they receive these documents, they read it, and they update their estimates. They take the information, but they do not actually input it to the database. So in order to use our model, what the claim handlers would need to do is exactly that. So they would have to read every document and then type in every single information that this document brought in, right, in their respective fields. So we provided a Flask app UI where they would just type in, they receive an update of the recovery process, they receive update on income, etc., and then they would have to type it in. And of course, they hated it, so they didn't want to use it. And at the end, by our intention to actually decrease the workload of the claim handlers, we created a lot more work for them. And this led us to an idea to try to actually get that information, so we need to fix that. So our approach was to try to extract this information from unstructured data, from the documents. So we would take the document and then take the necessary information from that document. So for that, we used the Watson Knowledge Studio API, and we did a small POC with one group of documents. We asked the claim handlers, okay, let's do this as a one-off thing. So you take these documents and just underline the needed information and set it to which type it is. So for example, this is basically the screen that they also see. In this part of the screen, each color refers to an entity type. So entity type is basically the variable in our machine learning network. So in this case, what we have is for example, the body part that was injured, the intensity of injury, whether the ambulance was there, whether the person was hospitalized, etc. So all the information that we would need, they would just underline and say this is this particular type. Finally, we would feed that into a neural network that is running behind Watson Knowledge Studio. And we would have a train model so that given a new document, we can extract this information and feed it to our neural network. That was the basic idea. And so the work exploded immensely. From solving the initial problem here, the work exploded so that we had to take so many steps in order to be able to make this useful. So basically, in order to be able to use our network, we needed to build a separate machine learning model for each document type, because it is very difficult to have a single model that will take just a generic document and extract information. So we built a separate model for each document type. Then, of course, it's not really useful to have to read the document and say, okay, this is the type of the document, and then feed it to the model. So for that, we also had to bring one more layer, and that is the document classification layer that would basically do a word embeddings of the document, and we trained the convolutional neural network so that given a new document, we could label it as being a medical type, lawyer type, or client information. And even that was not necessary because so many documents just come through the pipeline without being computer readable at all. That would just be images of text. So we had to add one more layer that would basically do the OCR, optical character recognitions of the documents, to make them readable for the tool. So I will quickly jump to the second example, but just to conclude with this one is that by solving the initial problem, we did manage to solve it, but we didn't achieve much. So it was not useful. Even though the model fulfilled all the business requirements, it was still not useful for the users. And I think we all, when developing models for the users, we all need to keep in mind that there may be many steps that we need to fix before the model becomes useful. So let me quickly turn to a second example, which is based on an example from banking industry, where we, like I said, the bank is the largest bank in Russia, and they invested heavily in data science, and they wanted to make every decision made based on the data. So they built this huge sequence of models, from propensity models, churn models, and they presented their relationship managers with outputs of all those models. And even though each of the models had really good metrics, really good Gini coefficients, and every metric that they tried, the models really worked and they were correct. But finally, the users didn't find them useful. The relationship managers were presented with too much information, and they could still pursue their own KPIs. So, given the propensity for different products, you will always pursue the product for which you will be evaluated, and that was simply the model was not user friendly. So that's why we proposed a different approach, where we would have only one model. So a single model that, given all the information, current information about the customer, and so current meaning like current balances, current products that they have, and also some socio-demographic information about the customer, and history of interactions with that customer, and all kinds of business rules and business limitations. So we feed all that into a single model, and for every client and every moment in time, we want to provide only single action. That, in the end, would lead that towards client lifetime value maximization. So that's very important, that this model is prescriptive with the objective to maximize lifetime value of every client. And so this really illustrates the change in perspective that we needed to take. So from the initial model being looking like this, that this is just an example. So for every product, for example, we would have to create a model that we could score we would need to score every single client and say whether they will accept that offer or not. While in our next best action approach, we focus on the customer and say, okay, with this probability it will take this model, with this probability it will take this product, etc. And we can make a path. So this is not a one-step thing that we are just focusing on one step in time. We are really looking at the long-term horizon and lifetime value, so that we can take multiple steps and create the optimal path for each client that will maximize its lifetime value. The way we did it was by, okay, this is just a kind of an introduction of the next best action. But the way we came about this is that to go from the traditional propensity models and really try to model the decision-making under uncertainty, because that is really what the relationship manager and the customer relationship manager is doing. He's trying to make a decision, and he's really he cannot be 100% confident about the outcome of that decision. So for that, the Markov decision processes are a very good tool to model decision-making under uncertainty, where a certain entity, it can be anything that we want to control. In this sense, we are kind of controlling the customer. It can be in some multiple states, and in each of these states, we can apply a set of actions, where each action is, with some probability, taking us to another state or keeping us in the same state. So I will give an example that our current state can be, for example, the sequence of products that the customer is using at the moment. Every action can be a different product. And with some probability, it can take us to a state where the customer acquired this offer product, or it can leave us in the state where the customer just didn't get it. So this is kind of the simplified description of Markov decision processes. In general, like I said, for us, a state is a set of features that describe a client in a given moment in time. Let's say we did it on a monthly granularity, so at a given month, is a set of features that describes the client. All interactions initiated by the bank are considered as actions. That is our control space is basically to apply a certain action. Those can be either product offers or some kind of service action, but any interaction that we make to a client is included in the actions, and these actions are heavily controlled by the business rules. So we do not have a full flexibility to contact every client every month with the same product, or to contact every client 2 months in a row for any reason, etc. So this action space is heavily influenced by these business constraints. And then finally, reward is basically what we get out of the successful outcome of our action. So some actions may result in just a zero reward, where nothing changes. Some actions may lead the clients towards an early churn, if we're spamming the client, if we are... Basically, every action that we make that doesn't result in a purchase of some kind is money lost, because on the one hand, we are investing our campaign money and resources for communication. On the other hand, we are using this valuable slot in time that we can, this slot in time where we can influence our client, and we're not successful. And now we have to wait for a certain number of periods before we can contact him again. So it's a very expensive to miss this opportunity, in my opinion. And so the way to solve these problems is, I will have to speed up a bit. The way to solve these problems is, this kind of Markov decision processes is Usually with some kind of a transition matrices where we know a set of state and we have a probability to end up in different state. However, since we dealt with such a large client base of like millions of clients, then our state space was kind of continuous. So we did not have like a distinct number of states where the client can be. That's one problem, and the second problem is that no, this is a different slide. Yeah, that if we would like to create clusters of the clients and make them into states, that we lose so much information from about that. So in that sense, we turn to reinforcement learning as a way to solve this kind of Markov decision processes. And in particular, not the reinforcement learning where we iterate through the process of a single client, but we take like a batch of clients. We take a large historical data set of clients that were in certain state at the moment. Some actions were applied, some interaction from the bank was applied on that client, and we see what was the reward of that action. And from that, in batches, we create a reinforcement learning loop that looks something like this. So finally, our QN function is the customer lifetime value after n months. So in our case, it was 3 years. And in order to get to our maximum client lifetime value, we take several steps and we iterate. Basically, in each iteration, output of each iteration is an input to the next iteration, etc. So it's a classical reinforcement learning framework where our Q function is simply a supervised learning model applied on a batch of data. The results were quite positive. Basically, in every client segment, we did achieve an increase of client lifetime value. And finally, when applied in reality, when applied in a real campaign, the model outperformed the traditional propensity models. And interesting thing is that it didn't outperform it based on conversion rates, because that was not the point, but it outperformed it based on the reward, on the revenue generated by organizing a campaign based on the outcome of that model. And so with all this, I would like to, I hope I exceeded a bit my time, but I hope I managed to convince you that here the problem is not in the granularity itself, the problem is not in the framework itself, the problem is that we have one more step missing, and that we need to keep that in mind when we are developing our models and trying to support our customers. And with that, I would like to thank you for your attention and be happy to answer any questions.
Thank you. Reminder once again to ask our questions via the following link. So it's dsc.network/Q/A/Tesla with a capital T. And we already have some questions here. So from your practice, what is the most challenging / time-consuming step, let's say, in the data science process?
Mm-hmm. Well, there are several. So the most challenging for me, being not from industries that we were discussing, the most challenging is basically this, being able to really understand the business and to develop a model that is fulfilling all the business constraints. But at the same time, that is the most rewarding, because you really learn how the world works. So if you apply that for, I don't know, from agriculture via financial industries to transportation, you really learn a lot about each of these industries, and that's rewarding at the same time.
Thank you. You had an example of this Russian bank. So do you have any results you can share with us, any follow-up of what happened after the project? So are the results sustainable and reliable for now?
Yeah, so they're still using so in 3 campaigns, they managed to achieve the return on investment on the whole development stage. How they are improving the whole model now is to check whether those business rules that I mentioned for communicating with the clients, to try to make them also data-driven. So their data science team took over the projects, and it's a living product, so they're still improving it.
And what happens when there's, let's say, a misunderstanding between the business side of things and the data science of things? I mean, I understand that they're not exactly 2 similar spheres. So how do you deal with those types of issues? And do they occur? How frequently, let's say, do they occur?
Unfortunately, they do occur, and then it's really a problem when we are far along the life cycle development of a product, and we realize that we are not talking about the same thing when we are mentioning, I don't know, evaluation, like I mentioned at the beginning. So it can be interpreted by everybody in a different way. So my only recommendation would be to avoid it by having having really frequent meetings. So I know that agile is now the word for that everybody likes to use, but I think it's really important to keep these weekly meetings and to share everything to prevent deviation when it's too late.
So to be within the same page, let's say,
Yeah.
we're from the
Yeah,
start.
yeah, yeah.
And going on this, can you give an example of how to communicate the project with the client for good acceptance? What sort of steps can you take to say, or one example, if you have one?
Yeah, so I think, for example, these two examples that I shared were kind of, especially the first one, the insurance company, is the finally that we presented a project that was really well adopted by the user. So some of the checkpoints that I make there is that the model is very prescriptive, doesn't give too much space for interpretation, and is kind of explaining everything that it presents, because it often the user has to, the model is defying user's intuition, user's experience. So the model needs to be really, really transparent for the user to say, aha, this is why, this explains this number.
Okay, thank you. Unfortunately, we're a bit out of time at the moment. I would also invite all of the audience to come and speak to our distinguished speaker during the break and afterwards. As for now, I would once again, on behalf of the conference, like to express our gratitude and thank you for your talk and to handle you this certificate of appreciation. So thank you.
Thank you. Thanks. Thank you.